Algebra 1, Post Chapter 10, Worksheet number 3. A reminder that you should have Worksheet 3. It's labeled D3 with the name, then specific name after that on my website. You should have that printed out and fill it out along with me. I do think that we'll pretty much do this worksheet together. There won't be a lot for you to do on your own. We're just going to fill this out together. I would say 80% or better of it will be done by the time we finish this video. Before I get to that, I want to remind you of some things that we did already discuss and kind of carry that into higher ordered functions or higher degree functions. So for instance, in chapter 6, we started with linear functions. This was your slope-intercept form, point-slope form, standard form of lines. And we know that a line, with the exception of a horizontal line, a line is going to pass through the x-axis one time, right? Those just being two examples right there, right? The only exception to that would be a horizontal line. Every other one is going to have a x-intercept, which when solving, so if this is the graph right here of y equals 1/2 x plus 3, when you go to solve 1/2 x plus 3 equals 0, you're going to get this number right here, whatever that is, as the solution. And in the exception, when it's actually parallel to the x-axis, that's when we get a no solution, okay, just to link up the graph with solving. And we even did use graphing as a method for solving back in chapter 6. Then when we carry that into quadratics in chapter 10, what you typically have is a parabola that passes through the x-axis twice, and we get these two numbers as solutions when we go ahead and solve a quadratic equation for that. Again, if this is just, and again, I'm just making stuff up, y equals x squared minus 2x minus 1, this is the parabola for this. I don't know if that's what the parabola to that I just said looks like, but you'd get these two solutions nonetheless. And that would be then the solution to 0 equals x squared, whatever I just said, okay? That wasn't the only possibility though, right? Parabolas can open up or down. That really doesn't affect the solutions, right? If I had a parabola that opened down, but it passed through those same 2 points, the two solutions would yet be the same. But a parabola can not touch the x-axis at all. This was the case of no solution. And a parabola can also, and again, they can open up or down, right? So I didn't mean to do that. It can open up or down, but if it doesn't cross the x-axis, that was the case of no solution. We did also consider the possibility where the parabola did just come down and touch the x-axis, something like this, and we can identify that as the only solution. There was the potential for two solutions, but it turns out that they end up being the same thing. If we solve it by another method, by factoring or quadratic formula, or using square roots, or completing the square, I think those were the 4 methods that we had in chapter 10. You'd have the potential for two solutions, and then they just come out to both being the same thing. If this is the number 3, you'd solve using the quadratic formula, and you just end up getting 3 and 3. Okay? Now, here's the thing. A cubic function, so that's something to the third power. Here we have first power, second power, third power. We're talking about the degree. If you've forgotten about degree, I would have you go back and look at chapter 9. I believe it would be in the first section of chapter 9. And we classified these things. Cubic is third degree, and cubics have the potential to cross the x-axis 1, 2, 3 times. Okay, now are you picking up a pattern? Degree 1, 1 solution. Degree 2, 2 potential x-axes or 2 solutions if it's an equation to be solved. Cubic, that's a degree 3, and there are 1, 2, 3 potential solutions. Now again, it doesn't have to be the case that there are 3. It could be that it's only 1. Right? This would be the only real solution here. In Algebra 2, we'll explain to you where the other 2 went. Okay, they're actually non-real solutions. We'll get into that about halfway through your Algebra 2 class. But there would be one, there would be guaranteed to be one in a cubic function because of the behavior of a cubic function, which is really the thrust of this worksheet right here, end behavior. This is what we're talking about. And yes, just like this parabola here touched on the x-axis, it can be the case that a cubic could do this, in which case it would have 2 solutions, 1 and then 2 here where it's tangent like that. Your former geometry students, you know what tangent is. Remember from chapter 12 in geometry where a line that just touched the arc of a circle was tangent. Same word here. This graph is tangent to the x-axis if there's only one point where it's touching. Now again, there is the potential for 3 because this is a cubic function. It just is the case that 2 of them got eaten up by this one point, and then the third one is here. Okay. Now again, see if you. And also, by the way, cubics don't have to go up, down, up. They could also go down, up, down. Just like quadratics can open up or open down, this could go up, down, up. That's end behavior, as in as x gets larger, the y is getting larger, but as x gets smaller, the y is getting smaller. Just the same, you could have a similar looking graph, but it could go down, up, down, like this, okay? And I'll let you speculate right at the moment to see if you think you know what would control that, okay? And then for quartic, quartic means to the 4th power, and it could cross the graph as many as 4 times. So something like that, across the x-axis, I mean, as many as 4 times. So something like this would be quartic, okay? But just the same as this one here, it could be only crossing 2. And again, in Algebra 2, we'll get into this in more detail, and you'll identify these as the real solutions, and then there ends up being in this type of graph 2 non-real solutions. Different topic for a different month, right? And again, you can have this tangent situation. I won't go through that again, but I will point out to you also that you could have a graph that doesn't touch the x-axis at all in the case of a quartic. So it might look something like this. Okay. Now I made that one to open down. I talk about quartics in the same way as I talk about quadratics. Open up, open down. Here you have open up. This one also opens up. This one open down. And in this case also, the one that I drew that opened down here, it didn't cross the x-axis at all. This would be a no real solution situation. And again, just to link it to something you'll learn someday in Algebra 2, there will be 4 non-real zeros to this. Okay? So now look, this is really great for background. Probably 75% or more of what I just explained to you is not relevant to this worksheet, but it's really great foundational stuff for you to understand as we actually get into simpler things on the worksheet. Okay, so here we go on to the worksheet now. And I did go ahead and put the scale in ahead of time so I could save myself some time. If you want to pause the video right now and enter these scales, I went by ones on every one of the x-axes, so that's why there's a 5 at the 5th spot. But then I changed them up based on what we're going to see on the graph. So this one's going by ones, this one's going by twos, right? 2, 4, 6, 8, 10. This one's going by fives. This one is going by twos again. This one's going by tens, 10, 20, 30, 40, 50, 60. Okay, and they're asking us to graph these, and it says draw 2 arrows to indicate the end behavior of the function as x approaches infinity and as x approaches negative infinity. Really, we're just talking about the arrows that you would put on a graph. Okay, actually, I'm sorry, I got a little bit ahead of myself here. I did want to show you one thing on the calculator too. So here I have graphed just the parent function for a quadratic. Here I have graphed the parent function for a quartic. Here I have graphed the parent function for something to the 6th power. And when I highlight them on my graphing calculator, that means that's what will show up. So right now, these bottom 3 will not show up. And I want you to just notice, it's going to graph x squared first, then x to the 4th, then x to the 6th. Notice what happens. So by color, it's going to be blue, red, black. Ready? Blue, red, black. Blue, red, black. Now notice a couple things. Number one, notice that they basically have the same behavior. They're both open, or they're all 3 opening up. They all 3 pass through the origin. That's not a surprise. 0 to the 2nd power is 0. 0 to the 4th power is 0. 0 to the 6th power is 0. So if I plug 0 in for x into any of those 3, the output is going to be 0. Notice secondly, though, that they got narrower as they got higher in degree. That also shouldn't be shocking, because if you plug in, let's just pick a number, 3, and you square it, you get 9. So your output, 3, 9 would be like right here on the blue graph. But 3 to the 3rd on the red graph, that's 27. That's off the graph. 1, 2, 3, and then 27 will be way up off my screen. 3, 27. And even bigger for, I'm sorry, not 27. It's 3 to the 4th, which would be 81. Check what I just said there. 3 squared is 9. We went to 3 to the 4th then, which would be 81. And then 3 to the 6th power is huge, right? So that's why that's happening. So as the degree gets higher, the graph gets narrower. Now, one other thing, you know that the blue graph is a parabola. That's unique to quadratics. The red and black graphs, while they behave like a parabola, the word parabola is not appropriate for anything but a quadratic. They have the same kind of shape, but they are not a parabola. Okay, now, one other thing. Let's take those three off. And this should have really been evident in the demonstration I did on the starboard there, but just the same, so you can see it on a real graph, it's going to go to the third, to the fifth, to the seventh. Okay, so in color, it's pink, green, orange. Pink, green, orange. Watch. Pink, green, orange. So in the same way, you might say, well, they got narrower, and they certainly did. Pink is the widest, green is next, and orange is the narrowest. But also notice that the end behavior is different. And this is the case with whether it's even or odd. The exponent, that is the highest exponent, which is the degree, if it's even or odd. Now, the graphs that I was showing you on the starboard there, those are complicated, right? A cubic that crosses the x-axis 3 times. Let me just take this off. Let me just take 5 and 6 off, and we'll just talk about the cubic. The cubics that I was graphing a few minutes ago, as I was drawing them out, yeah, they're more complicated, and they go up, and they cross to the x-axis, and then they come down, and they may cross it again, and they go up again. That's something like, 2x to the third minus 3x squared plus 9x minus 14, or something like that, where you've got a cubic term, a quadratic term, a linear term, and a constant. These are simple, and this is where we're really going to be living more than anything else on this worksheet. But do notice that if it was odd, right, to the third, to the fifth, to the seventh, for that matter, to the first, right, a line is going to have end behavior that behaves like this pink one more than it is going to be like a parabola where both ends are going up or both ends are going down. That's called end behavior. All right, now let's get back to the worksheet. And the first one there, y equals x to the third, well, we just saw this on the graph. We're just going to have to put this now onto this graph paper. And 0, 0, right? I'm just going to plug in 0. What happens when I plug in 1? 1 to the third would be 1. 2 to the third would be 9. So this takes you up to 8. 9 would be right off the graph right here. Okay. Oh, I beg your pardon. It's 8. You already knew that, didn't you? 2 to the third. Not 3 squared, but 2 to the third. Excuse me. It's 8. Now, -1. Be careful now, because we may have you conditioned to do quadratics, and you might think, oh, it's going to do this. Not so. When it's x to the third, and you plug -1 in, that's -1 times -1 times -1. That's -1 as an output. -1 in, -1 out. -2 in is like saying -2 times -2 times -2. That's -8. And this is all you need to draw a graph. I'll say the same thing about these as I did about parabolas, is that it is a curve. So try to show it's got some similar features to parabolas as far as curves. It's just that this branch is going up, this branch is going down. All right. Now notice the next one is x to the fourth, and it's also negative. So let's just do it orders of operation. Plug in 0. 0 to the fourth is 0. -0 is 0. You've got a point at the origin. Plug in 1. 1 to the fourth is 1. And then make it negative. That'd be -1. That would actually be here. Right? -1 will do the same thing, because -1 to the fourth is like saying -1 times -1 times -1 times -1. That's 1. But then you make it negative, and it's -1. So that would be here. And this is going to spike quickly, if you will, in the negative direction, because 2 to the fourth is 16, and then you make it negative. So here's 2, 4, 6, 8, 10, 12, 14, 16. Yeah, right to the edge is -16. You'll also have -2, -16. And this is holding consistent to what we talked about a few minutes ago about end behavior. This opens down. Okay, next one. Let's plug in a 0. Now this is interesting because it's got a y-intercept of 3. We'll do the best we can to estimate that. But let's just plug in a 0. 0 to the fifth is 0. Negative doesn't change it. It's still 0. Plus 3 would be an output of 3. So that's right about here. Do the best you can. This is 0, this is 5, so a little more than halfway is 3. Okay? 1 to the 5th is 1. Make it negative. It's negative 1 plus 3 would be 2. So that's going to be just slightly lower. I don't even know if I can really show that because they're so much close together. 2 to the 5th. I'll give you a minute. 2 to the 5th. It's 32. Make it negative. Negative 32 plus 3 would be negative 29. So that's 2, negative 29. So we're going by 5. So 5, 10, 15, 20, 25. Here's negative 30. We're just slightly short of that if I can show that correctly. Okay? That's all we're going to get in the positive direction. Now plug in a negative 1. Negative 1 to the 5th is negative 1. Right? When it's raised to an odd power like that, it's negative times negative times negative times negative times negative, which is negative. So negative 1, and then there's a negative in front of it, so that changes it to positive. So now we have positive 1 plus 3 would be 4. So we're here, and then negative 2. Negative 2 to the 5th would be negative 32, and then the negative changes negative 32 to positive 32, right? Because you had negative 32, so that's 32. Plus 3 is 35, which would be right here. And then do the best you can to show something that kind of resembles what we just saw in the calculator window. Something like that. Okay, I'll leave 4 for you to do, and then let's go ahead and do 5. 0 to the 6th is 0, negative 0 minus 2 is negative 2. Now that's very close to the origin because we're going by tens in this case, right? This is negative 10 already, so negative 2, you're going to have to estimate. 1 to the 6th is 1. Make it negative is negative 1. Minus 2 would be negative 3. I mean, that's almost identical based on the scale we have. I'm trying to make that slightly lower on a horizontal line than that point, but hard to do. And then 2 to the 6th is 64. So negative 64 minus 2 would be negative 66. Just about like that. And then same thing with negative 2. So this is a graph that opens down. Again, it's not a parabola, but it does behave like a parabola in that it opens down. Okay? 6 was actually kind of an accident. It's a repeat of number 3, so we can just skip that one. Please do number 4 on your own. I told you before that I will eventually post keys to these worksheets, but that's going to be for a few weeks, not going to be for a few weeks. So sit tight on that while everybody kind of does chapter 8 and then gets into this section kind of at their own pace over the summer. All right. Now, moving forward, it says fill in the table, and they're giving us these different ordered functions, these different degrees. Recall again in chapter 9 that it's the highest, from chapter 9, that it's the highest exponent that stands in for the degree of the entire expression. So this is a quartic, right? Though this is a cubic function and this is a linear function, we don't look at that. We only look at the highest degreed term, and that identifies what the degree of the function is. And this is a 4th degreed function. This one would be 2, this one would be 3, and this one would be 5. Let's go ahead and fill that in. 4, 2, 3, 5. Now, if you're paying attention to what we talked about at the very beginning, the potential for the times that it would cross the x-axis is the same as the degree. That means that the number of zeros, or really we should say the maximum number of zeros, as this heading says, is the same number. If you graphed this, the maximum number of times that it would cross the x-axis, and each of those is a 0, the maximum number would be 4. This would be 2, this would be 3, and this would be 5. Again, if you graph this, I'm not saying it would be 5, but it could be 5. It could go up, down, up, down, up, and each one of those different directions could pass through the x-axis. It has a maximum of 5 zeros. Now, leading coefficient. This is important. That leads something that goes right into the 4th and final worksheet of this little series here, is to understand what the leading coefficient is. And it's easy to see on these, but it's not as easy to see in the next worksheet. So pay close attention to this. It's simply the number that's in front of the lead coefficient. So this is assumed to be a 1 right here. This is assumed to be a -1 right here. You got negative x squared, that's like saying -1 x squared. This is a 1. Note also that all of these are in standard form. That's why I only have to look at the first term. Right? If they weren't, then I might want to rearrange them first, so I have descending order. This one would be a -3. Okay. Now, lastly, I did go ahead just in preparation for this and put the infinity symbol in place, so I didn't have to draw that for you 8 times and correct it because it's a little hard to draw on these sometimes. But what we need to put in front of them is whether it's positive or negative, positive or negative. So I'll put a plus or a minus in front of each one of these things. Hopefully you are familiar with what that symbol is. It means infinity. Okay. And we even say in the wording here, as x approaches infinity, f of x approaches what? Okay. So as we look at a quartic, just like we did look at a quartic in these two problems right here. Oh, no, just this one, I guess. That was a sixth power. Oh, these two. In these two problems, although you have to still do this one, quartic. And note that this one opened down. Do you think that this one's going to open down? No, this one's going to open up when you do this one on your own because there's not a negative in front. It's a positive x to the fourth. That one's going to open up. So on a graph like that, as x approaches infinity, meaning that, again, as x gets bigger, okay, so if this graph opens up, as x goes this way on that graph, what's happening? Well, it's raising, it's going up. So this would be positive. But also, let me just do it like this. It's going to be a graph that looks something like this, right? So what I'm saying is that as you trace along the function, as you let the x value get bigger, the y value is also getting bigger. Oh, but if you let the x value get smaller, the y value is still getting bigger. That's the answer to this. Positive, positive. And it is going to infinity. It's going up forever. Here you have a negative quadratic, right? Because it was degree 2. So you're looking at a graph. So this one goes with number 7. This graph is going to go with number 8. Now, I don't know what they look like, so don't hold me to whether they cross the x-axis, where they land. But it is a negative lead coefficient, so this is going to be a parabola that opens down, right? And with that, then, as x approaches positive infinity, meaning as we trace along the function going positive, it's going negative infinity. It's going down, in other words. And so is this one. As I go this way, it's going down. We're talking about end behavior here. This is the key word, end behavior. It's right on the worksheet. Okay. Quickly, here you have a cubic. Now that graph then would look something like this: up, down, up. Don't hold me to the positions of anything, but that's the general shape. And you see, as x gets bigger and bigger as it goes to infinity, as it really starts here and goes up forever, right? So that's positive. As x gets big, y gets big. But different from the other two, as y gets big, as x gets big, as x gets higher, one more time. As x goes negative is what I really should say. As x approaches negative infinity, what's happening? The y is also approaching negative infinity. Okay, now again, I say that's different from the first two because these first two are the same, both positive. These two are the same, both negative. But here you have opposite in behavior. As one gets bigger, the other gets smaller. They're essentially going away from each other. This is end behavior for an odd degreed function. The same thing is true with to the fifth power because it's odd. That's called a quintic function. So this would be negative, positive. Okay. I hope that was a good explanation. I got to move on to the next page because this video is going to get long otherwise. Remember, you don't have any homework, though, other than just a couple of problems that we're going to leave out from doing this. All right, so then we have a matching situation. Let's just read through it. It says, which choice describes each graph? The degree is odd and the leading coefficient is positive. The degree is odd and leading coefficient is negative. Degree is even, coefficient positive. Degree is even and leading coefficient is negative. Okay, so I wouldn't assume that you're going to use each one once. Okay, let's just answer the questions as they come. As I look at number 11, I'm going to suggest that is a cubic. Okay, now whether it's cubic or quintic or seventh power or ninth power, I really don't know that for sure. But it's at least cubic because it has 3 places where it's crossing the x-axis. So it's at least cubic, and more importantly, you must know that it's going to be odd. Okay, it's cubic or it's quintic or etc. because it's not quadratic because it crosses the x-axis 3 times. It's not quartic, 4th power, because that would have the end behavior going in the same direction. That's what we were trying to establish on that last activity. So this has to be odd. I've ruled out C and D. It must be A and B. Okay, now here's a key point. You must learn this by the end of this worksheet. It'll help you on the next one to know that if it's positive, it's up, down, up. And if it's negative, it goes down, up, down. That is the lead coefficient. Lead coefficient positive, it goes up, down, up. Lead coefficient negative goes down, up, down. That is just the case. And you can test that with as many graphs as you'd like. So where does that fit then? Well, that's A. The degree is odd, we already said, and the lead coefficient is positive. Okay? Now look at 12. Here you have end behavior that is going in the same direction. So right away I would rule out A and B. It must be C and D. Okay, and then you have something that's opening down. We know that's negative, right? So that's going to be D. The degree is even and the leading coefficient is negative. Now tell me what the difference with number 13 is from number 12. For the purposes of this question, there is no difference. It opens down, right? It's end behavior, same direction, opening down. This is also going to be D. This one's probably quadratic. This one's probably quartic. But as far as the 2 criteria that we were being asked about, they both have end behavior down. Okay, and then 14 is going to be C, opening up. It's kind of like it looks like a quartic like this one, but it's opening up. So the degree is even and the leading coefficient is positive. All right, wrapping it up here with just a few more things. Again, asking about the degree. The degree here would be probably 4. Now again, it could be 6, 8, 10, 12. Point being that it's even, and it looks like it's probably 4 because there are 4 zeros. Okay, so we're going to stick with minimum for the degree then is 4. Remember that the degree goes along with the number of potential zeros. Okay, so I see 1, 2, 3, 4. Not only that, we can identify, assuming the scale is going by ones here, that's what you should assume, we can identify what those zeros are. This is at -5, this is at -3, -2, -1, 0, 1, and 2. -5, -3, 1, and 2. Okay, here you have a degree 2 because there's 2 zeros, and they are at -6 and -3. If I'm going too fast and you need to stop and process this, just pause the video. 17, the degree would be 3. It's got 1, 2, 3. 3 zeros, or really what we want to use to determine this more than where it's crossing the x-axis, because that can be deceptive, right? If you had this graph and it was like this, it'd still be degree 3, even though it's only crossing the x-axis once. The determining factor there is how many different directions. We're going down and then up and then down, so it's 3. So degree 3, and this is at -6, -4, and 1. And then this is, let's see, 1, 2, 3, 4, 5, degree 5. And there are 5 zeros, right? So that was 5 different directions, or you might say 4 direction changes. We went up and then down, up, down, up. 5 is the degree. And those zeros are -6, -3, the origin 0 itself, 2 and 5. Okay? And then lastly, this is somewhat more of the same of the graphs that we started with. So let's just maybe do 2 of these. And it also does talk about the symmetry. So let's just do 19 and 20. And I'm plugging in 0. 0 to the 5th is 0. Negative is still 0. So there's a point at 0, 0. I plug in 1. 1 to the 5th is 1. And make it negative, that'd be -1. That is going to be so close to the x-axis, it'll be hard to even distinguish it. Okay, I think I did a pretty good job there, though. And 2 to the 5th is 32. This is why I picked the scale that I did. And then make it negative. So 2 -32 would be about right here. Okay, now if you do the same thing with negative numbers, -1 to the 5th is -1. Make it positive, that would be 1. That's going to be like right about there. And then -2 to the 5th is -32. Make it positive, and we're about right there. Okay, so do your best to draw a curve that passes through those points. and you've got it. As opposed to x to the 6th, where you plug in 0 and you get 0. You plug in 1 and you get 1. You plug in -1 and you get +1. Careful with that negative, right? Here, -1 to the 5th is -1 times -1 times -1 times -1 times -1, which is -1. And then the negative changes it to +1. Here, you plug in -1 and it cancels itself out because pairs of the -1s, -1 times itself, times itself, times itself, times itself, times itself, is going to give you 1. And then 2 to the 6th is 64. So because of the scale that I picked, I can actually fit that, and it's about right here. Same thing with -2 as far as height of this, and then draw the graph. Okay, now you all being geometry students already know about symmetry here. So the two answers, and I'll just leave this for you, the two answers are rotational or reflectional. You decide. Is this graph, does it have rotational symmetry or does it have reflectional symmetry? As in, is there a point that I could rotate about in which you'd get the same graph back if you rotated it 180 degrees or less? Hint, it'll be exactly 180 degrees. Or is there a line that you can put in place where if you reflect over that line, you'll get the same graph back? Okay, go ahead and answer that for all 4 graphs. Just finish these 2 and then answer that for all 4 graphs. And that really is a wrap for the worksheet. I left very little above for you to do. So that is worksheet 3. Thanks for tuning in.